Welcome to our video series, Easy Experiments to Understand a Complicated Earth.
Hi, I'm delighted to be speaking with you today. My name is Nicole. This topic I find interesting because it's amazing how we can perceive the color. Also, this one is related with the temperature, either with the color of our body and the color of the sky.
Are there only 7 colors? Why we don't see everything in white? The visible light spectrum is a segment of the electromagnetic spectrum that the human eye can view. More simple, this range of wavelengths is called visible light. Typically, the human eye can detect wavelengths from 380 to 700 nanometers. It's interesting how our world works. There are many things to understand, like the light or why is invisible spectrum wider? Well, let's create a spectrum. First, you need to fill the bowl with water. Put the bowl of water in a sunny place. It could be outdoors or near a window, so the sun can shine through the water onto the mirror. Hold the sheet of paper above the bowl and try to capture the spectrum with it. When we shine a light on the part of the mirror that's underwater, the light bends as it moves from air to water, but because the components of white light travel at different wavelengths, they bend to different degrees. These colors are reflected by the mirror, and these are which you can see on the sheet of paper. In daily life, we can find light spectrum. For example, it's easier to find a rainbow of the rain when we go to sea along the side of ship, or when we go out and spill gasoline. That looks like the third image. All electromagnetic radiation is light, but we can only see a small portion of this radiation, the portion we call visible light. Cone-shaped cells in our eyes act as receivers turning off the wavelengths in this narrow band of the spectrum. Other portions of the spectrum have wavelengths too large or too small and energetic for the biological limitation of our perception. Electromagnetic radiation is one of the many ways that energy travels through space. The heat from the burning fire, the light from the sun, the X-rays, a microwave, all forms of electromagnetic radiation. While these forms of energy might seem quite different from one another, they are related that they all exhibit wave-like properties. A wave has a throw, lowest point, and a crest, highest point. The vertical distance between the tip of a crest and the wave's central axis is known as its amplitude. The quantity known as the wave's frequency refers to the number of full wavelengths that pass by a given point in space every second. The SI unit for frequency is Hertz, which is equivalent to per seconds. As you might imagine, wavelength and frequency are inversely proportional. That is, the shorter a wavelength, the higher the frequency, and vice versa. This relationship reflects an important fact: all electromagnetic radiation, regardless of wavelength or frequency, travels at the speed of a light. Here you can see the frequency and the wavelength of a light wave. The last quantity we will consider is the period of a wave. A wave's period is the length of time it takes for one wavelength to pass by a given point in space. Mathematically, the period t is simply the reciprocal of the wave's frequency, f. Now that we have an understanding of some basic properties of waves. A photon is the elementary particle or quantum of light. Photons can be absorbed or emitted by atoms and molecules. When a photon is absorbed, its energy is transferred to that atom or molecule because energy is quantized. The photon's entire energy is transferred. The reverse of this process is also true. When an atom molecule loses energy, it emits a photon that carries an energy exactly equal to the loss in energy of the atom's molecule. This change in energy is directly proportional to the frequency of photon emitted or absorbed. One of the things that chemists study is how different forms of electromagnetic radiation interact with atoms and molecules. An example in daily life is the Earth's atmosphere. Generally looks blue because it contains particles of nitrogen and oxygen, which are just the right size to suck your energy with the wavelength of blue light. When the sun is low in the sky, light travels through more of the atmosphere and more blue light is carried out of the beam of the sunlight before it reaches your eyes. Only longer red and yellow wavelengths are able to pass through, often creating a breathtaking sunset. What we are seeing when we see an object is reflected light. When light hits an object, some wavelengths are absorbed by the object and some are reflected. Light of different wavelengths looks like different color to us. When we see an object of certain color, that means the light of that color's wavelength is being reflected of the object. For example, when you see a red shirt, the shirt is absorbing all the colors of light except for the red color. The frequency of light that we see as red is being reflected and we see the shirt as red. Black and white are a bit different from other colors. White is a combination of all colors, so when we see white, the object is reflecting all the colors of light. The same. Black is the opposite. When we see a black object, that means almost all the colors of light have been absorbed. As objects grow harder, the energy emitted by shorter wavelengths changing color before our eyes. A flame on a blowtorch shifts from reddish to bluish in color as it exaggerates to burn harder. In the same way, the color of stars tell scientists about their temperature. There are seen wavelength ranges in the visible spectrum that coordinate to a different color. Each visible color has a wavelength. As you move from red to violet, the wavelength decreases and energy increases. Here are the 7 from shortest to longest wavelength. Those sources most often seen in large spaces, such as stadiums and warehouses, or in street lights, automobile lights, and floodlights. Now it's possible to answer the question you had at the beginning about the light spectrum. Light is one of the type of electromagnetic wave that humans can see. Electromagnetic radiation can be described by its amplitude, wavelength, frequency, and period. When all the wavelengths of the visible light spectrum strike your eye at the same time, light is perceived. Photons carry discrete amounts of energy called quanta. This energy can be transferred to atoms and molecules when photons are absorbed. Atoms and molecules can also lose energy by emitting photons. EM waves interact with the molecules of the objects. Some wavelengths are reflected or absorbed and our eyes interpret the color. Studying this topic allows us to create theories, interact with our world, try to understand it, and improve it. Here I let you some interesting questions and where you can answer it. There is another way to do the same experiment. We need the same materials as before, but now we add a lamp. 1. Shine onto the part of the mirror that's on the water. 2. Tilt the mirror until you see the colors. The only difference between them is that in the first one several arches are formed and the figure is different.